work for this. So starting with these particular 8 moves, we can rotate it 90 degrees once, twice, and 3 times. So here we have the first 32 moves. And I actually did them in 2 different colors because these make 2 different specific systems, which can just be connected by legal Knight's moves. So looking at the black system, this creates a system that is called the right diamond system because it looks like right diamonds, and the red system creates a system called the left diamond system. So just keep those shapes in mind. And so as for the other 32 moves, we have to start out with another set of 8 moves that looks like this. So we're going to rotate it 90 degrees 3 times once again. And I put them in 2 different colors because now we have 2 new sets of systems. So we're going to connect them using Lego Knight's Knight's moves. The blue one creates a right square system, and the green one creates a left square system. And so the reason why these are helpful, well, now we have 4 systems. We have left and right diamond and left and right square. So if we overlap all these systems, we can actually see that they're going to touch, don't freak out. It will actually touch every single square on the 8x8 board. And the only problem with this right now is that the 4 systems are independent and they're not connected. And that's kind of where your own logic comes in. So we're just going to show you a quick video of how we solve the Knight's Tour using the systems. So we start out with the 8x8 chessboard. I'm just going to split it into 4x4 quadrants so that it's easier to follow. So what I do is I pick the upper right square in the first quadrant and to start in. And I notice that that is in the right diamond system. So I start in that system and I'm going to start going around and I'm going to solve that system to completion just using where those diamond shapes touched in that original thing. So I get to the end of this, and now one of the rules is after you end a diamond system, you have to move into a square system. So I'll look for a legal Knight's move that can go to the square system. I find that, and from there I'm going to solve that all the way around to completion. And once I get to the end of this one, following that rule, I have to go into the other diamond system, which is the left square system. Left diamond system. I'll follow that to completion. So I do that, and I can't get back into the first quadrant. So what I'll do is start with the left diamond system and the 4th quadrant, go backwards, and then everything starts to come to me very quickly. The only system left is the right diamond system, or the right square system, and I follow that around to completion, and you have a solved Knight's Tour. Alright, so this method works, and hopefully most of you understood it, and you can all use it just if you know those shapes, and you can apply it to where you started it. But this doesn't have a whole lot of math behind it. A lot of it is coincidence. So the first person to actually put forth the solution to a Knight's Tour is Bernard Euler, and I'm going to call him Euler at some point today by mistake, so sorry. Before I actually go into how he solved his method for the Knight's Tour, I'm going to go into something called graph theory, or Euler networks, which I'm sure some of you learned in geometry. Now this started out with the Konsberg's bridge problem, represented here. And that's where you have 4 land masses, and there's 7 bridges going across them. Now the point is to cross all 7 bridges only once and get to all 4 land masses. And nobody can solve it. So Colin Euler, he turned this into a more graphical representation that looks like this. Each point is called a node and represents one of the land masses, and each line is a vertice, which represents one of the bridges. So Euler has these rules for graph theory on the side. First one is that a network with no odd nodes is traversable. And what I mean by an odd node would be if you have a node here and there's 3 vertices coming off, that makes it odd. So an example of this first rule would just be a triangle. It's got 3 nodes on it. Each node has 2 lines or 2 vertices coming off of it. There's no odd nodes, and which makes it traversable. You can draw around it without taking your pencil off the page. Second rule, a network with 2 odd nodes is traversable. An example of that is just 2 points with a line in between them. Each one has an odd vertice, and you can just draw straight to it. Now, the final main rule of graph theory is that if you have one or greater than two odd nodes, the network, which is just this system like this right here, is not traversable. And that's the case with the Collinsberg's bridge problem. Here we have an odd node with 3, odd node with 3, odd node with 5, and odd node with 3. That's greater than two odd nodes, so it's not traversable, and therefore the Collinsberg's bridge problem cannot be solved. However, if I were to add, let's say, another bridge right here, creating that vertice, this could work because now we have 2 even vertices right here and 2 odd ones, which falls into the second rule. So that's just kind of the quick background to graph theory. And now for this next one, I need you to keep calm and not freak out once again. So we have this. This basically just represents the 8x8 chessboard, and it's been turned into an Euler network. So up in the upper left, we have the first square of a chessboard. It's represented by a node, and it has 2 lines coming off of it. Those 2 lines represent the 2 legal knight's moves that you can make from that position. Right? Yeah? And that's why it has a 2 inside of it. That's the number of options you can make from that position. And then from there, you can see as you get closer to the center, there's more options for the knight to move just because there are more squares around it. Now, if you look at all the possible options from all these nodes, you're going to notice that this actually doesn't comply with graph theory because we have 8 odd nodes, the 3's going around the sides. So technically, this shouldn't be traversable. And that's because the Knight's tour is a little bit different than Euler networks. Euler networks, you're trying to cross every vertex once, and you can touch the nodes as many times as you want. But with the Knight's tour, you are really just what you're trying to do is touch each node only once, and you can cross whatever vertices you need to. So the actual proof for the Knight's tour was put forth by a person named Schwenk. And he had the rules that Ben's about to talk about real quick. That actually proved whether or not a Knight's tour works.
So one of the rules is when m and n are both odd, and then the other one is when m equals 1, 2, or 4, and when m equals 3, and n equals 4, 6, or 8. So that is why an 8x8 chessboard works.
Right, because it doesn't violate any of this. So, that was kind of a side note, but so we're going to go back to how Euler actually solved the Knight's tour. Now, what do you do? Another scary picture, not that bad. What you would actually do is start with an incomplete Knight's tour. The numbers just represent the moves made. So this is the first move, second move, third move, and he goes all the way around just doing it by hand and guessing. Now he gets to the 62nd move out of a total of 64. So this leaves him with 2 spaces left, A and B. Now, given, oh, hello. Okay. Alright, so given the legal Knight's moves of that L shape, there's no way we're going to be able to get to A and B and complete this tour. So what Euler would do is actually try to rearrange this network in such a way that it does work. So what he would first do is list all the possible moves that the 62nd move can go to. So you can see from 62, we could go to 9 using that L shape, to 53, 59, 61, etc. List all those possibilities, and like Ben said, there's a total possible of 8. And then he does the same for A. Lists all the possibilities from that space. That's move number 32, 8, and 42, etc. So, from these 2 sets of numbers, he looks for consecutive moves. In this case, we have the moves 9 to 10, 53 to 54, and 55 to 56. So, in this case, we're just going to choose 9 to 10. And what he would do is actually disconnect the move from 9 to 10. You can see that there. Reconnect 10 to A, and reconnect 9 to 62. So as you can see, we're getting a bit closer, but we still have that point B all the way down there that we need to get to. So he does the same thing. Lists all the possible moves from A, which are the same, pretty much the same as last time, 32, 8, 52, 42, and then lists all the possible moves for B, 57, 25, and 43. And now he's going to look for, again, consecutive pairs. So in this case, it's only 57 to 58. So this takes his final move. He disconnects the move from 57 to 58 that he originally made, reconnects 57 to B, and reconnects 58 to A, and then you have a solved Knight's tour. Now, this method is a bit tedious, and it'd usually be worse because there'd usually be a lot more open squares left, but we just did 2 for the sake of time. Now, Ben is going to explain to you the actually quickest way or most efficient way to solve this problem using computer science in its most classical form.
So, Like David said, the knife square is a common problem given to computer science students, and there's a few ways to do it, but the most popular and efficient way to do it is using Warnsdorf's rule. And the main idea behind it is that you proceed to the square with the least amount of onward moves. So if you start here, which square would you go to? And so you do that throughout the entire program. The next idea is that you do not return to a square that has already been landed on, so that the computer doesn't, or you get rid of the square that's been moved to, so that the computer does not return to a square you've already landed on. And you can see that here. You might notice that this space on the diagram that Berk used before is right here, and the numbers inside the onward moves are not the same here. They're one less because you get rid of this option. The last idea is that if there are the same number of options, you can choose randomly. For example, in this different scenario, if you start in the same place and there are 3 4s, which are the smallest numbers, you can go to either of them, which creates a random solution. And so I tried making my own program, and so I first printed out a 8-byte chessboard and labeled it 1 through 64, and then chose a random square. I went with 29 because it's pretty much in the middle, and I found that these were the possible moves it could go to, these numbers. And if you add and subtract 6, 15, 17, and 10, you will be able to find those numbers. But there are some problems by doing this. If you are, for example, on space 2, adding 15, 17, and 10, that works. If you add 6, though, you end up on space 8, which is not a legal knight move. And if you subtract any of those numbers, you get a move that is off the board. And so I took care of those issues with an if statement, which I will explain. So if for all of the squares that are shaded yellow, they do not run into the problem with negative numbers, and which are basically just moves that are not even possible. And so in the code, this is what it looks like. If that doesn't make sense, it's basically just if any of the 8 possibilities are less than 1 or greater than 64, do not make it a possibility for the original square. So that section of the program goes through and creates all the possibilities for all 64 squares. It then finds the least available moves for a proposed square to find the next square, and following Warnsdorf's rule. And it removes that next move, the next move's number, from future possibilities, so that the program does not return to squares that have already been landed on. And it continues that for all 64 squares. So to show you the end results. There we go. So that's what the program looks like. Would you like to pick a number from 1 to 64? Just
Yeah, let's start. You guys want to start off?
17. Alright, so that'll start on square 17. I'll just change this variable right here. There you go. And there you go.
So basically that's just really quickly computing the number of possibilities and taking at least one. And that's all.
Excellent.
And just to emphasize that that one idea of Warnsdorf rule that you can choose a random square if they have the same amount of least possibilities, then I'll run it again on the same square, and it will make a difference. So if you can just remember the last one.
So cool.
Which one? Right?
Right.
Good job, Berk.
Wait, no.
Oh, hold on. You do. that's just one of the various ways you can do the Knight's Tour, and that works because of, if you go back to Schwenk's theorem, it fits those restrictions. And so, finally, so what? Besides this being a very cool problem that I know all of you are going to go home and try to solve, it's going to be like the new Sudoku, I promise. This problem really, it can be solved in a lot of different mathematical ways. Ben and I only covered 3 of them. But it really revolves around the idea of how to most efficiently travel a specific route and get to every single point. So this can apply to various things with traveling, whether that be flights or mail delivery even. It all comes back to kind of the basic theories used in this problem. So thank you to Jamie for helping us out with this. And there's one more practical application of this problem.
That was wonderful. The last part of the evening is to become a tradition that we always ask our guest speaker to provide a little commentary and offer some gifts to the students.
Oh, I guess that's me. Well, I guess my commentary has to be,